Greetings. We're going to discuss kinematics in one dimension. So let me proceed. Okay. One-dimensional kinematics. This is a perfect example. The starting point, as you can see, is from here. Okay, and the particle moved. Okay, to the positive x direction. Within 1 second, it moved from 1 meter to 3 meters. Okay, therefore, the 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 displacement from 0 to 1 second is 2 meters going east. And then after 1 second, from the third meter, it moved to the fourth meter. And from the fourth meter, it moved backwards towards the negative x direction to the second meter. Okay, so this is one-dimensional kinematics. One-dimensional kinematics doesn't only talk about the positive direction. Okay, we also have the negative direction. In this case, we have the the direction on the positive x-axis of a Cartesian plane and the negative x-axis of the Cartesian plane. Okay, so here we're going to discuss the following. Alright, so before describing a motion, you must set up your um, point of origin, okay, to identify if you're going to a positive direction or to a negative direction. Okay, the distance is the total length of travel. I already discussed this on the vectors, angles and vectors. Okay, while displacement is the change in position. Okay, I also discussed this on the angles and vectors. Now let's differentiate average speed and velocity. When we say average speed, it is the distance covered over an elapsed time. Okay, so while average velocity is the displacement, therefore we need to put a direction. There are cases that the movement of a particle is not um, identified or illustrated in a linear form. Okay, sometimes it looks like this. So therefore, we have the instantaneous velocity. Okay, instantaneous velocity is, for example, what is the instantaneous velocity when time is equal to 1 second? Okay, according to this graph, okay, you're gonna take a look at this graph and you will see here on the x-axis that you have the time. Okay, so you're gonna take a look at 1 second. Okay, where will it hit on the graph? Here, and then you will identify the magnitude of that position. Okay, on this graphical representation, it seems like at 1 second, our instantaneous velocity hits 25 or around 25 meters. Okay, so at that instant, we have 25 meters as our position. Okay? Therefore, we can solve for the instantaneous velocity. Let us now proceed with acceleration. Acceleration is the change in velocity over a period of time. Okay, and it is expressed using this formula. Now, when we say acceleration and deceleration, you should not be confused because um, when we say acceleration, we're talking about an increasing speed. And when we say deceleration, we decrease the speed. So when you say increasing speed, both of your acceleration and velocity has the same direction of travel. Okay, but when we say that, let's say you hit the brakes, okay, so your movement is currently going east, but when you hit your brake, your acceleration goes to the negative direction or to the west direction. So therefore, acceleration and velocity are in opposite directions. So that's when you call it as deceleration. So what happens when acceleration and velocity has the same direction? Okay, what happens is the velocity increases, but when acceleration and velocity are in opposite directions, therefore velocity decreases until it will come to a stop. Okay, so this is our working formula for the computation of the final velocity if the acceleration is constant. Okay, when the acceleration is constant, therefore, here is our working formula. We were in VO is the initial velocity plus acceleration multiplied with time. Okay, so here are other formulas incorporated with the motion with constant acceleration. So we already have discussed this one. Sorry, that that was taken from this one. So this came from this formula. Okay, to get the average velocity, just simply get the average of the final plus initial. Okay, and we have position as a function of time. Okay, we're gonna be using this formula wherein XO stands for initial position. Okay, and for the velocity as a function of time, we're gonna be using this formula. Okay, so we have a VO squared, VF squared is equal to VI squared plus 2A delta X. Delta X signifies, or it means that it is the change in velocity or final minus initial. Let's have example number 1. Okay, so Ima Cortez is approaching a stoplight moving with a velocity of 30 meters per second. The light turns yellow and Ima applies the brakes and skids to a stop. If Ima's acceleration is 8 meters per second squared, then determine the displacement of the car during the skidding process. So we're looking for the displacement. Okay, so here is our solution. So our initial velocity is 30 meters per second, and our final velocity is 0 because you need to come to a stop. So we're looking for this displacement. Okay, so everything is given. Now we're gonna be using this formula, Vf squared is equal to Vi squared plus 2a d, wherein d is the change in position, delta x. Okay, but we put d here as our variable, therefore we're gonna be using d here for our solution. Okay, since our final velocity is 0, here's our initial velocity. Now why is it negative 8? Because we hit the brake, therefore it's deceleration. Okay, should be on opposite direction, so that's why it's negative. Okay, therefore we're gonna be having the value of t as 56.25 meters. Next, Ben is waiting at a stoplight when it finally turns green. Ben accelerated from rest at a rate of 6 meters per second squared for a time of 4.10 seconds. Determine the displacement of Ben's car during this time period. So we're given here the initial velocity as 0 because from rest, okay, with an acceleration of 6 meters per second squared and a time interval of 4.10 seconds. So we're looking for the displacement as well. So here is our graphical representation. So our initial velocity is must be 0. Okay, this must be 0. Okay, and then the time is 4.1 seconds and our acceleration is 6 meters per second squared. Now, we're going to be using this formula. Delta x is equal to VIT plus 1 half AT squared. But delta x is represented by the displacement D. Okay. So applying the given parameters, initial velocity is 0. So this would become 0 plus 1 half acceleration time raised to the second power. Therefore, we're going to have displacement as 50.43 meters. Next, a car traveling at 22.4 meters per second skids to a stop in 2.55 seconds. Determine the skidding distance of the car. So we're still looking for the distance. So says here, our initial velocity is 22.4 meters. Good. And then skids to stop. Therefore, our final velocity is 0. Time is 2.55 seconds. So we're looking for the distance it traveled. Now, we're going to be using this formula. So that's VI plus VF over 2 times time. Or it was taken from the formula velocity is equal to distance over time, right? But we have the average velocity here. This is our formula for average velocity. Okay, and average velocity multiplied with time is distance or displacement. And we have 28.56 meters as the distance it traveled. Okay, now we're talking about instantaneous velocity. Okay, so the position of a particle moving along the positive x-axis varies in time. According to the expression, x is equal to 3t squared, where x is in meters and t is in seconds. Evaluate its position at 3 seconds and at 3 seconds plus the change in time. Letter C. Evaluate the limit of delta x over delta t as delta t approaches 0. Find the velocity at 3 seconds. So here is our solution. For letter A, we are given this formula. Therefore, just going to substitute P time for us 3 seconds. So 3 multiplied with 3 squared, we're going to be having a position as 27 meters. Next, at 3 plus delta t, okay, so we don't know yet what is delta t, therefore it's a variable. So we're just going to substitute 3 plus delta t for the time, okay, and we will have this equation. You just simply multiply this one, distribute. Okay, so as you can see, it's squared, therefore you have to apply or expand this one.